All right, so let's continue our discussion of boundary value problems. And we're going to focus on a few interesting cases with a specific focus on understanding stress concentrations. Some, some exposure you may have had to this in the past. I don't know why I spoke like Yoda for that, but you may have seen this before, obviously, but we're going to take a deeper dive on this and understand how does the theory of elasticity equip us to analyze these situations where we may have concentrated loads or we may have localized features in the geometry of some part or some member that cause stresses to localize in those regions and achieve higher states of stress than throughout the rest of the member. So having the theory of elasticity equips us to be able to analyze these situations where the stresses may be distributed in this non-uniform way, in this more complex way, and being able to resolve that is precisely what we intend to do in today's lecture. But before we dive into that, I wanted to finalize our discussion of the problem from last lecture, where we were looking at this simple cantilever beam, and we'll kind of go through that. But we were looking at this simple cantilever beam where we assumed we had some distribution of stresses defined everywhere on the boundary of this particular problem. And we needed to have stresses defined everywhere on the boundary in order to have a well-posed boundary value problem. If we didn't specify everything, then there's any number of different possible solutions we could arrive at. So in order to satisfy having a unique solution, we had to be particular about what specified stresses we have everywhere on these different surfaces. So provided we have these boundary conditions, we went through the exercise of actually trying to solve for what is the resulting distribution of stresses internal to this body, given the externally applied stresses or the boundary conditions. And we used this thing called the Airy stress function, which was this rather magical concept invented by some guy named Airy, who supposed that there existed some function, the Airy stress function, whose partial derivatives with respect to x and y gave us these components of stress. And who's to say where this idea came from? We just suppose that we have a function that gives us these stress components in this particular way. And really the magic of the Airy stress function is that if you do this, if you choose to represent your stress field in this way through the Airy stress function, then you automatically satisfy the equilibrium equations. And remember, all of this was really specialized to the case of two-dimensional or plane stress or plane strain elasticity. In the case of analyzing members and other kinds of two-dimensional structures in this way, it actually didn't matter whether we were looking at plane stress or plane strain if all we really wanted were the stresses, and if we assumed that the body forces are roughly negligible. So if we do that, if we use the Airy stress function, then we don't really have to do anything special to satisfy equilibrium. The only thing that we do need to verify is compatibility. And the procedure that we adopted to actually come up with our guess for what the stress field should look like was by assuming one of these stress components. Maybe we come up with some reasonable guess for any one of these three different components of stress. We integrate it twice to get some guess of what we think the Airy stress function looks like. And then given that guess, we can take derivatives of that assumed form for the Airy stress function to get the other stress components. And then we can go through and verify compatibility and enforce our boundary conditions on the stress in order to make particular that specific or generic form for the Airy stress function that we've postulated. And we did that last lecture, so I won't go through all the details. But what we found was this. We got a stress distribution that looked kind of like this, that had a linear variation of stress through the depth of the beam, and it kind of varied along the length. And we had a quadratic variation in shear stress through the depth of the beam. Okay. It all came from assuming a form for the Airy stress function that looked kind of like this. And it turned out to be rather trivial to verify that this particular solution satisfies compatibility. We could plug in all these different values, but it turns out rather trivially if you plug in these different terms. And in fact, any Airy stress function constructed from some combination of polynomials that look like those shown at the bottom of the screen here, if you pose the area stress function to be some combination of those polynomials, then you'll always get compatibility, satisfied for free. So kind of a convenient thing there. But we found this solution for the stress field, but was that the end of the story? Once we have the stresses, maybe that's all we really care about. Maybe we don't really care about finding out what are the other solution fields of interest. But this is elasticity after all. And why don't we just go through the exercise of figuring out, given the stress field, can we then figure out what the other fields are? The strain field, using our plane stress constitutive relationship, which we use because we're using an assumption of plane stress for thin bodies that have a relatively thin thickness in this, through thickness dimension. So assuming plane stress, we can use our constitutive relationship to relate in-plane stresses to in-plane strains. And again, this is the special case of plane stress elasticity. So slightly different than the relationship you would get for three-dimensional elasticity in the stress-strain relationship, or even for plane strain. And from this, we can then devise what are the resulting expressions for the strain field, which look kind of similar, but they're also slightly different. So clearly, the shear strain field also has this quadratic variation, much like the shear stress distribution had. And we also have the axial strain distribution that varies kind of linearly through the depth of this beam. But we also have a transverse strain, epsilon YY, which is kind of the through thickness strain, and it's non-zero. And what this really implies is that depending on, well, what the Poisson's ratio of the material is, if Poisson's ratio equals 0, Poisson's ratio implies that if you stretch some piece of material longitudinally, it'll contract laterally. So what really this expression for the transverse epsilon YY strain is saying is that if I have some Poisson's ratio that's non-zero, such that when I pull on the material, it will contract laterally inward, or if I push on it, it'll expand out laterally. What this is saying is that if I have some, longitudinal extension of material fibers along, I guess you could say along the axis of the beam, if they're stretching out longitudinally, then also they have to basically contract laterally. Same thing on the opposite side of the beam. If fibers are being compressed axially, then they're also expanding out laterally. And that's all captured within this fully, in this case, two-dimensional expression for the deformation experienced by small chunks of material anywhere inside of this beam. So we capture all of this interesting phenomena now that we have this theory of elasticity that equips us to be able to analyze and solve these types of problems. But let's go the final step. Let's, given this strain field, now figure out what is the resulting displacement field. And we can do that rather simply, as you did in a previous homework assignment. You can take the individual components of longitudinal strain, epsilon XX, epsilon YY, integrate each of them respectively with respect to X and Y, and you'll get some supposed solution for what you think the displacement field should look like, its two components in the X and Y direction. But that's not it. In general, if I were to integrate these two functions with respect to X and Y, I have to really introduce some additional generic function or constants of integration to account for the fact that really, if I integrate some function epsilon XX with respect to X, there could be some function that I could add to UX that depends on Y. And when I take the derivative again of UX with respect to X, that function just goes away. So I recover epsilon XX. But if I were to try to compute what is the shear strain now, given these assumed forms for the displacement field, UX and UY, my shear strain field, remember what it was? What was the shear strain, at least in this two-dimensional case? What was the displacement strain relationship? How did I get shear strain given the displacements? Yeah, it's written here. But for those who kind of need some refresher, the idea of the shear strain being basically some kind of combination of the mixed derivatives of the ux displacement partial derivative with respect to y plus the uy displacement partial derivative with respect to x, and then a factor of 1/2 thrown on there. So from that, you can get the tensorial description of shear strain, or if you like, you could call it also the engineering shear strain, which is just twice that tensorial epsilon xy. So from that, we have now this extra constraint. We can assume some forms for A and B. We can then take partial derivatives of these assumed forms for ux and uy to come up with what is, my expression for the resulting shear strain. And it should agree with this distribution of shear strain that we determined from our elasticity solution, from our Airy stress function. And you might think, well, hey, wait a minute. Didn't we already satisfy compatibility? Didn't we already get this for free, once we posed our Airy stress function such that it looks kind of like this, and I got my stress components, and if it satisfies compatibility, do I really need to do anything extra to enforce this condition that if I pose these forms for ux and uy, then do I really need to check this extra constraint on the shear strain? And the answer is yes. And it has to do with the fact that while you might satisfy the stress field, being compatible, it doesn't necessarily connect it back to what is the displacement field that gave rise to that particular strain field and subsequently the stress field. So to make that guarantee, we do actually have to verify that our assumed forms for the displacement field do in fact satisfy this extra relationship, which is almost tantamount to saying that indeed, whatever displacement field we choose still has to satisfy compatibility. So at the end of the day, nothing comes for free. If you have to actually find the displacement field, you do still need to verify this and enforce it explicitly. All right, so if we take these assumed forms for A and B, functions of y and x respectively, and just to kind of back up a little bit, we can take these integral terms with respect to epsilon xx and epsilon yy. You'll notice epsilon xx depends on an xy term, so its integral with respect to x gives me something that looks like x squared times y. This epsilon yy term, when integrated with respect to y, looks like a term that involves xy squared. And that's precisely what we get when we integrate those two terms. But we still have this a and b that we need to solve for. These generic functions, we don't know necessarily what their form is at this point. All we know is that we need for the resulting shear strain computed from this displacement field to be the same as the shear strain that we computed from our Airy stress function solution. So we can put this all together and basically take these two expressions, compute their derivatives with respect to y and x, sum them together, and we get something that looks like this. A relation that imposes some extra constraints on what particular form A and B need to have. Now, take a moment to look at this expression and verify for yourself that if I have some function, let's say A, that depends only on y, and if I look at this whole expression, there's some terms on the left and right-hand side of this expression that involve, let's say, x squared, y squared, and then there's a constant term, an h squared over there. So really, if I'm looking for some way of maybe relating the terms that appear in this equation to what should show up in my function A as a function of y, I can safely say that any of these terms that involve x squared really shouldn't influence my chosen form for what this function A should look like. And conversely, this function B, which depends only on x, shouldn't depend on these terms that involve y squared. So we can safely say that those are not associated with one another. And from that, we can kind of pose what we think these two functions might look like given these extra constraints, given what terms actually show up in this equation that relates the Airy stress functions given solution for what the strain distribution should look like, the shear strain, and given our assumed solution for ux and uy, what the resulting shear strain should look like. So equating those two things basically says that the sum of these two derivatives, derivative of a with respect to y and derivative of b with respect to x, has to be equal to these three terms that involve y squared, x squared, and a constant involving h squared. So if we assume this, then we really say that really a as a function of y should be kind of like, this term integrated with respect to y to give me back a. So if I have some term that involves y squared, I can basically say that a should be something that looks like y cubed. So when I take its derivative, I get back this very y squared term. And same thing for b as a function of x. If I have a term that depends only on x here, I take its integral with respect to x, I get this term, such that if I take derivative of b with respect to x, I get back that very term. So we've kind of hammered down at least these two contributions to what these two functions should be, satisfying this relationship, but there's still this leftover constant term that we need to account for. And in order to account for it, we basically have to say, let's introduce some extra terms in both a and b. They both may have some contribution to this constant term. And we'll just kind of label those coefficients as, let's say a sub y and b sub x, which are linear terms relative to y and x respectively. So when I take the derivative of each of these two functions, I get a sub y plus b sub x on the left-hand side, and just this leftover constant term expressing this requirement, basically a constraint on what the values of these two constant terms need to be. And who knows, maybe there's some extra constant that drops out when we take the derivative of both a and b. The true constant of integration, if we were to have assumed that if I take the integral of epsilon xx to obtain ux, really there should be a constant of integration there, but in the case of a multivariate function, it's a function of integration. Okay, so now I have these assumed forms for a and b. And if you're feeling like you're getting lost, don't worry too much. I think in terms of what I'll ask you to do in the homework on an exam, a lot of the time we're not necessarily interested in finding these solutions for the displacement field in this particular fashion. But it's illustrated to at least go through this process once, so you understand more or less what are the steps, if you ever have to do it yourself. In any case, we have these assumed forms for a and b. Now, really, the question is, we still have these four remaining constants of integration, and we only have really one, let's say, equation that imposes any constraints on what the values of these unknown constants should be. So we have one equation, four unknowns. Really what we need is three extra equations so that we can be more specific and determine what these remaining constants should look like in order to determine a unique solution to this boundary value problem. And the way that we do that is, again, we use our boundary conditions. This time, however, we use our displacement boundary conditions. We didn't need the displacement boundary conditions when we were solving for the stresses because we were totally complete and specific about what the distribution of stress looked like on the boundary of this domain. Now, however, if we're trying to find displacements, we have to dig up those old displacement boundary conditions, these constraints that I was a little bit funny about when I defined them. I'll kind of reflect on exactly how these different terms come about, but it's somewhat similar to how you might constrain, let's say, a cantilever beam by taking some individual point, some concentrated point right on the end of this beam and saying, I'm going to hold this point fixed. I'm not going to allow it to displace in the x direction or the y direction, and I'm not going to allow it to rotate either. So those three conditions, preventing rigid motion in the x and y directions and preventing rotation, are effectively what these three expressions are saying. The displacement at this point should be equal to 0 in the x and y directions, and also this kind of funny representation of basically the partial derivative of ux with respect to y has to be equal to 0, as tantamount to saying that this line segment, oriented somewhat vertically, can't rotate. That's basically what this equation is saying. And you can kind of stare at this and rationalize why exactly is that the case. But you can think of the rate of change of ux varying with respect to y as being an indication of how much this line segment is oriented relative to vertical. And that enforcing it to be equal to 0 is basically equivalent to saying keep it straight up and down. All right, so now we have indeed 4 equations. These 3 boundary conditions for the displacements, plus the other one that we had that came from that relationship between enforcing compatibility between the strain of the area stress function and the strain from our assumed forms for ux and uy. And we can use these 4 equations to solve for these 4 remaining constants, things that we don't know. You can do this any way that you like. In the end, you get something that looks like this. If we take these assumed forms for ux and uy, and we just evaluate them at these different locations, specifically at this point, if we say evaluate ux at x equals L and y equals 0, I get basically just a naught. And my boundary condition says that the displacement at this point has to be equal to 0, which is equivalent to saying that this single constant, a naught, has to be equal to 0. You can do the same thing, go to uy and say at this point, at x equals L, y equals 0, uy has to be equal to 0. And you'll get another expression that's slightly more complicated involving the other 2 constants, bx and b0. And then finally, the expression that says that the rate of change of ux with respect to y has to be 0 gives you a final expression that relates a sub y. So 4 equations, 4 unknowns. This one's not so bad. You could probably do this just by substitution and doing a few extra tricks. If it were a little bit more complicated, you might have to solve a system of equations, which is not so appealing. But it's something that I'm sure that you could do, or you could rely on your calculator to help you do it. All right, so once we have these different constants, we can solve these 4 equations for those 4 unknowns, and we get something that looks like this. The final expression for the displacement field looks kind of ugly. It's this huge expression involving all these different polynomial terms, and there's not a lot of intuition that you gain by sitting around just staring at these equations, as I'm sure you're probably already getting fatigued with the amount of equations that you've seen thus far in today's lecture. So rather than just dwell on equations, let's actually take a look at a graphical representation of these solutions and try to reconcile it with our intuition and our existing understanding of how we think these systems should behave. So if I were to draw out what the deformed configuration of this plate would look like after it's been subjected to the applied loading and you apply the displacements, it looks kind of like this. Now, let me just ask you off the cuff, does this look right to you? It's an open-ended question. I mean, is there anything kind of funny about this that you maybe weren't expecting to see? Given your understanding of how you understand beam theory and other kinds of descriptions of how beams behave, what was the classical description of beam bending behavior from Euler-Bernoulli beam theory? Yeah, there's some interesting effects going on here that you could probably see. What I'm kind of like hoping to, there's some conditions that were inherent to Euler-Bernoulli beam theory, which is kind of the classical beam theory that you may have been previously exposed to. But the idea is this: Euler-Bernoulli beam theory, the classical beam theory that you would use in your, strength of materials class, assumes the following. It assumes that if you have a beam that's relatively slender, that is to say that the depth of the beam is relatively small compared to its overall length, then ultimately, if you have some cross section that you can draw originally such that it's perpendicular to the neutral axis of this beam and planar initially, then after deformation, Euler-Bernoulli beam theory states that this particular cross section should remain perpendicular to the deformed neutral axis, and it should also remain planar. That's Euler-Bernoulli beam theory in a nutshell. And maybe there's some displacement going on, but in general, the cross sections remain planar. They remain perpendicular to the neutral axis. Do you see anything in this image that disagrees with some of the assumptions of Euler-Bernoulli beam theory? And if so, what are they? Yeah, it doesn't remain perpendicular. That's certainly one. And it's kind of hard to verify it without like taking a close examination at what exactly is going on here. But it is actually true. This image doesn't do justice to it, but that's exactly right. These cross sections aren't necessarily remaining perpendicular. So rather than being strictly perpendicular to this axis, and maybe it's useful to look at what's actually happening at the end here, it looks maybe more like, I don't know, this, where it's not quite a right angle. It's kind of like the cross section is actually, deformed. It's not perfectly perpendicular to the neutral axis. So that's one thing. That's one thing that's different. Is there another thing? And it's a little subtle. It's kind of hard to see from far away. What do you think about, let's say, the end of this member? It's originally planar, right? And then after deformation, is it still planar? No, it's kind of warped. It's got this strange S shape to it. And I think maybe you were mentioning that. It kind of has like this curvy behavior. But really, if we had truly plane sections remaining planar, that would be fully described by what's in this blue dashed box. It assumes that there's a linear variation through the depth of some kind of relative displacement in the x direction that kind of follows maybe the rotation of some blue dashed line that stays perfectly planar, maybe not necessarily perpendicular to the centroidal axis, but certainly planar. But really, it's this extra term in magenta here that depends on y cubed. So y cubed, what does a function that looks like y cubed look like? Yeah, it kind of looks like this. It kind of looks like what we have up here, where the cross section is starting to warp, possibly due to, who knows, maybe shear deformation effects or other kinds of phenomena. But in general, the important thing to note here is that we've captured this phenomena. We haven't made any assumptions, unlike Euler-Bernoulli beam theory. Much as Euler-Bernoulli beam theory gets a lot of stuff right, it doesn't capture the full picture. The theory of elasticity, however, approaching the solution of these problems in a fully general way, actually gives us a much more detailed description of what's going on that includes these interesting features. Now, what I want to point out also is what's going on with the tip deflection. Who can maybe even you recite from memory, what's the tip deflection of a cantilever beam subject to some kind of point load at the end? I think I'm hearing murmurs of it. But, from what I can recall, it's something like 3EI over L cubed, or rather PL cubed over 3EI. I guess it depends on which, orientation you have it at. But PL cubed over 3EI gives you basically the tip deflection of some cantilever beam subjected to an end load. Now, is that what we get when we evaluate this tip deflection? When we evaluate what's the y deflection at this particular point? Not quite. We do actually get PL cubed over 3EI. It's in there. It's in there, but it's there's something else going on here too. there's this extra term. And what's interesting is that this extra term really is proportional to h squared. In fact, if we take a moment and look at some of the terms in this hunk of garbage that is this collection of equations, we'll notice actually some interesting things, that there are certain terms that depend on things like h squared, y squared, or y cubed, which if we were to take a moment and say, well, what would happen if we were to try to replicate Euler-Bernoulli beam theory, given this existing solution that we've come up with? Can we somehow recover Euler-Bernoulli beam theory by imposing some conditions that replicate the assumptions? And remember what the primary assumption of Euler-Bernoulli beam theory was. It was this assumption of slenderness, that the members were relatively long compared to their transverse dimension. So the depth of the beam was relatively small. That's kind of tantamount to saying any of these terms that involve h squared or y squared, y cubed, and so forth, imagine those terms are relatively small, especially compared to any terms that depend on L squared or L cubed especially. So their contribution to each of these different equations can be basically regarded as negligible. And if that's the case, if we take this assumption that let's just get rid of all those terms that depend on these higher order, h squared, y squared terms, get rid of them, what we find is we actually get back exactly what we would have obtained if we had proceeded just with classical Euler-Bernoulli beam theory. That's pretty cool. And really, it should be a good confirmation that, in fact, our theory of elasticity isn't just giving us totally nonsense results that don't agree with what we would expect to see in reality and our intuition. It is actually in agreement with some of these more classical analysis methods. In fact, you could think of Euler-Bernoulli beam theory as just being a special case of taking these elasticity solutions and subjecting it to some additional constraints on, assumptions of slenderness ratio and other things like that. So you get back everything that you would want to have. So you should have confidence now that, well, this is quite interesting, but it's still, I think, worthwhile to consider what exactly happens in other scenarios when you don't have that assumption, when you relax the assumption of, relatively large slenderness ratios. And I won't kind of go into the details here. I will instead invite you after class to go ahead, and you'll find in Canvas under the files page, you'll find a subfolder named MATLAB scripts. And in it, you'll find this particular MATLAB script that generates all of these different figures. All you have to do is run it, and it'll spit out all these different figures. And what's cool about it is you can also go in and modify a few of the different parameters. You can modify things like what's the length of the beam versus what's the depth of the beam, and even what's the loading. You can change the material parameters if you want to, and you can see what happens to the deformed solution under these different situations to try to reaffirm and develop your intuition to say, what exactly is the limit of Euler-Bernoulli beam theory? And what happens as you kind of like shrink this thing further and further and further into almost like a squat, in this case, just like a square plate, basically. In which case you kind of see some combination of things. You see bending going on, certainly as you would in a classical beam, but you also see just kind of straight up shear deformations. It's bending, but it's also just shearing. And that extra term that accounted for the extra thing beyond PL cubed over 3EI, the extra amount of deflection is actually due to that shear deformation occurring. So all these things can be accounted for just by kind of going through our theory of elasticity, constructing these very general solutions. And the other nice thing about the theory of elasticity is it gives us these expressions for the displacement field, the strain field, and the stress fields as functions of position. And it really is helpful, in my opinion, to visualize these things. I'm a very visual learner, so it helps me to actually see the stress fields. The book doesn't provide a lot of visual. I wanted to provide you at least with some illustration of what these different functions look like, because if you're just staring at functions all day, it doesn't really give you a lot of intuition. But for example, you can take a look at this figure that illustrates the XX stress, or the axial stress variation through the beam. You can see that near the supports, there's kind of like relative maxima on the extreme fibers of the top and bottom fibers of this beam, where it's kind of a maximum negative value in compression on the top and a maximum tensile value on the bottom in tension. And then as you kind of go along the length, it sort of tapers off until eventually you have zero axial stress on this kind of end here. And then certainly along the neutral axis, it's just zero stress. So it all agrees with what we understand and hopefully what we assume. Same thing with the shear stress distribution. It varies quadratically. It's zero at the ends, but achieves a maximum right in the middle, but it doesn't necessarily vary as a function of axial coordinate x. So all very nice. I encourage you to take a look at this and just explore, experiment, have fun with it, try to gain a better sense of what's really going on in these different types of problems. So elasticity gives us these insights. We have to do a little bit of post-processing to interpret the results, but I'd rather have this than just kind of hope that Euler-Bernoulli beam theory is going to be sufficient for solving some problem, because sometimes it's not. Sometimes you do have these squat beams or components that can't really be properly idealized through Euler-Bernoulli beam theory, and you do really need to invoke some of these more general approaches. Okay, so with all that, let's now move on to really the major topic of discussion today, which is stress concentrations. So hopefully, if you've been kind of like dragging a little bit, it's been a long day, it's been a long week for one reason or another, now is the time to concentrate. Hopefully without too much stress. But before we can get into the subject of stress concentrations, a lot of the solutions that we're going to derive are going to be still using Airy's stress function to come up with solutions to mostly plane stress problems. However, we can no longer use our classical nice XYZ coordinate system for solving some of these problems. We could do it, but it actually makes it a lot harder to do. So instead, oftentimes, solutions to problems that involve these classical stress concentrations usually involve changing our definition of the coordinate system from a classical Cartesian or XYZ coordinate frame into a cylindrical or polar coordinate frame, which is probably something that you've seen before. Obviously, there's no tricks here, nothing fancy going on. We're just defining a cylindrical coordinate frame that can be parameterized in terms of some kind of radial coordinate and some kind of angular coordinate, both r and theta, if you like. So we can express the representation of the stress tensor, for example, in terms of components oriented relative to some coordinate frame, x, y, z, right? In plane stress, all we care about is x and y, so that makes it a little bit easier. In the case of polar coordinates, remember our stress transformation equations that we derived all the way back in chapter 1? Well, now you know why we did some of that. It's partly to set up further developments using polar coordinates. So if we want to represent what's the state of stress on some block in a cylindrical coordinate frame, where now we're considering some stress block that might be oriented at some relative angle theta away from the original x-axis. Now we can use our classical stress transformation equations, here represented in terms of matrix, vector, or tensor products, in order to come up with our transformed components of stress relative to this now r theta coordinate system. Okay, so nothing too fancy here. We've already kind of gone through some of that. The only thing that I'll kind of introduce as sort of an additional novelty here is to say in our classical Cartesian coordinate frame, we described positions within the body through this coordinate, we'll call it capital X, which is really just a vector that contains, let's say, two coordinates, x and y, in a two-dimensional coordinate frame. Now, if we wanted to transform that representation of our xy coordinates into equivalent cylindrical polar coordinates, we need to come up with some kind of coordinate mapping or a transformation between these descriptions of cylindrical versus Cartesian coordinates. And one relatively simple way to do that is to just say, well, these x and y values, assuming I know what some r theta coordinates are for a given point measured relative to the origin of the coordinate system, I can come up with what are the values for x and y just by saying r cos theta and r sine theta. Those are my xy coordinates expressed in terms of r theta or polar coordinates. Fairly simple. We could do the reverse. We could actually come up with an inverse mapping, given some values of x and y, figure out what are the corresponding values of r and theta in my polar coordinate frame. And I could come up with some equivalent or inverse mapping that looks kind of like this. Now, I'm going to be a little bit funny and suppose that I can also lump these two coordinate parameters, r and theta, also into a vector, much like I did for representing my coordinates as a vector, capital X, boldface. I'm going to call this thing psi, or you could think of it as a set of parametric coordinates, or variables, coordinates, if you like, that parameterize these positions x and y. And in general, I can represent both x and y as functions of both r and theta, or as this vector, this 2D vector of values, psi. All right. Now, if I wanted to compute other quantities, things like, let's say partial derivatives with respect to x, or partial derivatives with respect to r and theta, how I do that really depends on my choice of coordinate frame. And there's a couple different ways that you can actually transform between different representations of partial derivatives with respect to x and y, and corresponding partial derivatives with respect to r and theta, by exploiting precisely these coordinate transformations or coordinate mappings. Now, I suspect that going into the details of all this wouldn't really be particularly helpful or illuminating to you. So I'm not going to really go through all the details of what will follow next. I'll just say that it's possible to take these corresponding representations for, let's say, x in terms of r and theta, come up with some kind of relationship between what are the partial derivatives with respect to x versus partial derivatives with respect to these parameterized coordinates, r and theta, and also come up with maybe some relative mappings between these two different operators. In general, that operator is sometimes called a Jacobian, which is somewhat like the deformation gradient, the thing that we talked about a long time ago, where if you can parameterize the position of some deformed coordinates in terms of another set of undeformed coordinates, then that coordinate mapping gives you a way of describing basically a partial derivative of this output coordinate with respect to the input coordinate. And that partial derivative is precisely the definition of a Jacobian, basically, or the Jacobian derivative of some set of coordinates with respect to another set of, in this case, parameterized coordinates. So using the Jacobian, using some of these different relationships, we can do a bunch of nasty transformations. Now, again, I'm not going to dive into all the gory details here. The book goes through it, but in a way that isn't also particularly illustrative or illuminating. All that I will say is that if we wanted to transform our existing representation of our equilibrium equations that are originally expressed and formulated in terms of our Cartesian coordinate frame, so in terms of an xy coordinate frame, if I have my equilibrium equations expressed like that, the question is, how do I transform that set of equations into now the context of a polar coordinate system? Does it look any different? Is there anything unusual that comes about? These are the questions that are ultimately answered through this analysis. And unfortunately, it is rather complicated and probably not worth dwelling on. So again, the idea is we can leverage a lot of these notions of transforming between coordinates, do a bunch of fancy derivations, and there's a bunch of things that you can show to basically come up with eventually this, which is the equivalent representation of what are the equilibrium equations in polar coordinates. So the thing to take away here is that, recall, we had our stress components originally oriented relative to an xy coordinate frame. Now we have stress components oriented relative to this kind of rotated block, where maybe we have an r direction or a radial coordinate direction that is kind of going outward, relative to this block, and a theta direction that's kind of going circumferentially around some radial distance. Now, we can represent the different components of stress as different components of normal stress acting on these different faces of this rotated block. This normal component of stress acting in the radial direction is precisely this theta RR component of stress. This circumferential direction of stress component is the theta theta component of stress. So normal components of stress in the radial and circumferential directions. And then the shear components of stress on these faces of the block are precisely the sigma r theta components of stress. Okay. So really, if I'm referring to different components of stress in a polar coordinate frame, they should be sub-indexed not by x and y, but now by r and theta. And it depends on, where exactly are you in this circular arc? This is the most vexing thing about polar coordinates. The fact that, technically speaking, if you had Cartesian coordinates, it doesn't matter where you're sitting in the universe, x, y, and z always stay the same. In a polar coordinate frame, it depends on what point you are. This kind of representation of the local r, theta, and if you want, z directions, actually depends on, what the angle theta is. So in fact, the representation of what direction is the RR direction depends on what angular coordinate are you at. And that introduces all of the complexity that we thankfully just kind of skipped over so that you don't have to worry too much about it. The main thing that you should take away from this expression is that we get equations that involve the RR, R theta, and theta theta components of stress. They involve partial derivatives of these components of stress with respect to the two different parametric coordinates, r and theta. Okay. And they involve the body force terms acting in the radial and circumferential directions. Self-weight, if you like. But we also get some weird stuff that shows up. We get terms that look like sigma theta theta minus sigma RR divided by R. Where the heck did that come from? Or, you also have this minus 2R theta divided by R. And again, precisely where these terms show up is the subject of the previous derivation. All that you need to know is that the challenges of cylindrical polar coordinate frames being dependent on, where are you, and the coordinate frame itself rotating as you change angular coordinate theta. That's precisely why you get these extra terms. It's kind of an unfortunate side effect of working in polar coordinates that you have to have these more complicated and not so easily remembered expressions. But at the end of the day, you can still justify it in terms of, well-established, derivations, if you like. And if you're curious about it, I invite you to go back and go step by step through those derivations. All right, so if we have this expression for equilibrium, we can also extend our definitions of transformations between Cartesian and polar coordinate systems to not just come up with what's the resulting equilibrium equations, now in polar coordinate frame. We can also come up with what are, let's say, expressions for an area stress function that is posed not in terms of x and y, but rather in terms of these cylindrical polar coordinates, r and theta. And we can come up with proposed solutions for problems defined in terms of a polar coordinate frame and come up with the resulting expressions for components of stress, the RR, theta, theta, and R theta components of stress defined in polar coordinates, as also partial derivatives of this area stress function thing. And it's possible to show that all of these expressions, even though they're expressed in terms of R and theta, fundamentally, you could transform them back into an equivalent representation that depends not on R and theta, but on X and Y. And you would get back the original expressions that we had previously. So in fact, these are all totally equivalent expressions to everything that we had previously. It's just the nastiness of polar coordinates that makes it look kind of like, now you have partial derivative of phi with respect to R, plus a term that involves speed with respect to theta twice. And some of these terms have, 1 over r or 1 over r squared appended here. And the compatibility equation now looks quite a bit more complicated. It involves a bunch of other terms that are kind of hard to digest if you're just kind of staring at it. People have spent a very long time trying to come up with solutions to these very types of problems in polar coordinates. Unfortunately, I don't think it's particularly illustrative to go through exactly step by step how people came up with these solutions. Again, it really comes down to how do you choose this value? And you can spend a lot of time basically just guessing and checking different iterations on what you think the area stress function should be, figuring out then what are these resulting values of stress, plugging it into the compatibility equation, trying to verify that it satisfies compatibility while also enforcing all your boundary conditions, and it's just a mess. It's a lot of, just trial and error, and people have spent a lot of time trying to figure these things out. What I think is more illustrative is to consider existing answers to curious problems, I think, of interest to us. And to expound on that, let's suppose we looked at our very first boundary value problem now solved within a cylindrical polar coordinate frame. Now, the problem we're going to look at is actually kind of hopefully a useful one. Suppose, even though I say it's useful, it may not sound like it will be. But suppose that I have a semi-infinite plate. Now, I know you're going to say, semi-infinite, how can it be semi-infinite? I'm supposing that there's maybe some plate or some kind of object that has relatively large dimensions, okay, but local to some particular point on the edge of this plate. Let's just zoom our attention into this single point. And let's suppose that at this localized point on the edge of this relatively large plate, we apply some kind of concentrated force. And that could come from any number of different sources. It could come from, I don't know, if we're talking about a plate here, it's important to reflect that this is really not like this is not some representation of an elastic half space as you would have for like, some kind of structure sitting on top of soil or something like that. It's really more appropriate to think of this like maybe the top surface of a beam whose depth is relatively large and length is relatively large. And on top of this beam, maybe we have a concentrated load. And what we want to know is if I put this concentrated load, truly a concentrated load, it's singular at this point, what is the resulting distribution of stress inside of this beam local to this region where I'm applying the load? And does it give rise to any problematic stresses local to that area? That's kind of what we want to know. Certainly this can happen all the time. If you have, some member that's being loaded with a point load, you did this all the time in mechanics of materials and in statics. You set up a beam, you put a point load on the beam, and you said, well, there's a point load there. I don't care exactly what the stresses are surrounding that point where I'm applying the load. But I want to invite you to think about this. What would really happen if we tried to apply a concentrated load here? Now that we're equipped with the theory of elasticity, just conceptually, what do you think would happen? Yeah, you would have like a huge amount of stress acting at this point. In fact, what would be the stress at this point? If you have some force applied at this point, what's the stress underneath that point? Yeah, eventually, I think you're right. It would probably fan out. It wouldn't just stay at this one concentrated location. As you kind of like go further and further down and further away from this point, it'll start to distribute throughout the plate, and it'll be kind of distributed over a finite area. But immediately underneath that kind of point of application, if it is truly at a point and not necessarily distributed over like an area. Say again? Yeah. Yeah, it would have to be infinite because technically speaking, if I'm applying it at a point, I'm applying a force per unit of like 0 area. which by our definition of stress would imply that the stress would blow up. It has to achieve an infinite value. Now, you might say, that's wrong, right? Like, that can't happen in reality. Well, we're working with a mathematical idealization. And this is really where the limits of elasticity, come to their end. It's important to acknowledge that even though we can construct and pose these types of problems, are they really physically meaningful? Can we even reproduce these scenarios in real life where we have a truly concentrated load at a singular point? That's like a single mathematical point. We can certainly set up and solve the problems, and we'll do that, but I want you to think about the validity of this kind of answer. The book kind of glosses over it, but it does make an important caveat in presenting the solution to this type of problem. It says that while what's happening in the local vicinity of this point isn't going to be exactly right because, technically speaking, there should be a force actually distributed over a finite area. It's impossible to define a truly concentrated force like that. But a little bit further away, as you move a little bit further away from that concentrated force location, now you'll start to get some answers and solutions that are still reflective of what the physical reality would look like. So we can't trust what's really happening at this point. It's just impossible to do, and the answers we get wouldn't make any sense. You get infinite stresses. But just a little bit further away, now we can maybe use that to our advantage and do some engineering on that. So just bear that in mind, that these types of problems are inherently mathematical in their construction, but they give rise to still some useful engineering insight. Yeah. How far away? Well, that's precisely the subject that I'll hope to conclude on today. But to kind of cut to the chase on that, there's this thing that maybe you've heard of called Saint Venant's principle, which basically says that you can kind of replace, and maybe this is a good opportunity to explain exactly how we are going about this solution. We can replace some load, it doesn't matter how it's represented. In this case, assume that the load is represented as a point load. You can replace that load by some equivalent loading. And as long as those two loads, let's say some concentrated load versus some distributed load, as long as they're statically equivalent, as long as the net force between those two different representations of effectively the same net load is the same, then far enough away from those loads, the solution fields will look basically the same. So it doesn't matter whether you're truly representing it as a point load or as a distributed load. Far enough away, it looks the same. How far, though, kind of depends on things like the geometry of certain objects. Saint Venant was really interested in problems that looked at, prismatic members or structural members that had relatively large dimensions. And I think the main rule of thumb that Saint Venant came up with is that if you have, let's say, concentrated loads at the end of some long, slender member, and let's say that member had some characteristic depth h or something like that, then it usually is maybe like 1 to 2 or so, depth measures away from that kind of localized force. That's how far you would need to go before things kind of smooth out. And it doesn't really matter whether you're representing it as a point load or not. But it fundamentally does depend on things like geometry and other things like that. All right. So for this particular problem, we are going to have to be a little bit more creative in how we come up with the boundary conditions for this. Suppose we did actually consider this as an infinite plate. How we actually define boundary conditions on an infinite domain is kind of anybody's guess. Because what exactly is the boundary of an infinite domain? We can certainly define what are the boundary conditions on this top surface. It has to be such that, there are no components of traction acting on this top surface. So the normal component of stress and the shear component of stress has to be 0, except for, at this point of application of loading. But we can still represent that, I guess, in terms of, let's say, sigma theta theta, which is basically the normal component of stress anywhere on this kind of like top surface, as well as sigma theta r, the shear component of stress, have to be 0 all along that top face. All right, well, something else that's kind of useful to think about is we could consider maybe not necessarily taking equilibrium on this infinite plate. Let's make the problem a little bit more tractable and say, let's actually take equilibrium on a small chunk of the plate. I don't know, cut out some kind of semicircle, and then pose our boundary value problem in terms of now this distribution of stress on some kind of finite radius semicircle. We could do that. We could then say, let's come up with boundary conditions now on the semicircle. And for the sake of argument, let's just assume that these boundary conditions kind of look like this, where maybe there's a distribution of stress on the boundary of the bottom of the semicircle that is strictly normal to that boundary. So we assume a solution that has a strictly normal stress distribution on this bottom surface, no shear stresses. And maybe we also have it such that, that radial stress is 0 at the top faces and maybe achieves a maximum directly below the load. It's semi-plausible, it's semi-realistic. This is essentially how the book goes about deriving this. So we can come up with these boundary conditions, and we have to also impose some constraints on the values of, what this distribution or assumed distribution of stress needs to be, such that it is indeed in equilibrium with that applied point load. So we have some loose constraints on what exactly this stress distribution has to look like, just so that it balances with the applied loads. And the goal of this whole analysis is really then to come up with what is the distribution of stress in this body, given these boundary conditions. We can use our Airy stress function approach now in cylindrical polar coordinates to come up with a solution, but we'd have to sit around and guess what we think that, Airy stress function would look like now in terms of r and theta. It turns out that some clever people figured out that there are certain limited forms for what this Airy stress function can look like, such that it always satisfies compatibility and, obviously satisfies equilibrium for free. But these, genius folks came up with these limited representations for what the Airy stress function should be and reduced the amount of work they had to do to come up with some guess of what the Airy stress function looks like, just by looking at, those limited subsets of candidate functions that satisfy all these conditions, along with the boundary conditions. And without going into details, the resulting function that some folks came up with looked something like this. It has dependence on r, it has dependence on theta, and if you take its derivative, quite remarkably, you get stress components that look kind of like this. They certainly satisfy the boundary conditions. In fact, the theta component of stress and the shear component r theta of stress are both 0 everywhere, such that we really only have a strictly radial distribution of stress. So you can kind of think of the stress distribution looking like there's only, if you look at any block within this semicircle, it'll look like there's some kind of component of stress strictly aligned going straight towards the point of application of the load. So all, any components of stress that are pointing inward kind of cancel with each other in the x direction. And all the vertical components have to balance with this net load P. And you can use that balance of forces to then figure out what this kind of, maybe unspecified coefficient C needs to be. And you can solve for it and satisfy equilibrium by construction. So if we take this particular solution, assumed solution for the Airy stress function, but we can confirm it satisfies equilibrium, it satisfies our boundary conditions, it satisfies compatibility, well, it has to be a solution. Okay, well, it's a solution to some problem. Is it the solution to our problem? Well, we got to be creative in how we set up this problem. And again, coming back to the notion of Saint Benant's principle, how we exactly define these boundary conditions is sort of undefined. There's any number of ways that we could have chosen to represent this distribution of sigma RR stress on this boundary, but it turns out it doesn't really matter. Saint Benant's principle says that, like, far enough away from how we define these boundary conditions? If what we want to know is kind of like interior to this domain, then how we define those boundary conditions is irrelevant. So if we picked, let's say, some semicircular plate whose radius was quite large, and we just defined some boundary conditions that we know at least satisfied this kind of equilibrium condition in a global sense, then we could just pick any darn distribution of stress on this boundary that we wanted. And interior to this domain, solutions will look the same far enough away from the boundary, according to Saint Venant. So we can proceed along those lines and just say, well, it's a solution to some problem. And if we take the plate to be large enough, then it's a solution to any problem, assuming that we're far enough away from these boundaries. So in some ways, you can fudge your representation of these problems and still use rather general approaches that kind of employ these tricks, if you will. All right, so let's actually take a look at what the stress distribution looks like. And unfortunately, the colors on this are not great. I would invite you to also maybe take a moment to view the slides after the fact. We might be able to turn off some of the lights or something here. See if that works. At least that's a little bit better. Okay, so now take a look. Hopefully you don't fall asleep. Take a look at what this stress distribution looks like. Directly under the point of application of this load, which is denoted by this red dot here, you'll notice the stresses really are quite large. And in fact, they kind of zoom off to infinity. It's really impossible to show that, especially in this kind of numerical representation and graphical setting. But in fact, as you get closer and closer to this dot, the radial stress, which I'm plotting as a function of depth downward and axial coordinate and all that stuff, the radial stress grows and grows until it reaches this infinite value directly under the point of application of loading. But further away from the loading, as I go further and further down, some of your intuition comes to bear on understanding what's actually going on in this problem. Certainly, further away, the stresses start to distribute out. So if we looked at what's the stress maybe along some kind of cut plane below the surface of that kind of point of application, now the stresses die off actually quite quickly. And what's interesting is that you can kind of think of the stress distribution representing the magnitude of that radial stress as being basically constant along each one of these isocontours. So I plotted this as sort of like an isocontour plot, such that at each one of these color levels or color gradations, the value of stress is relatively the same at that particular value of stress. And you'll notice that this contour plot looks sort of interesting. It looks like a collection of concentric circles stacked on top of each other. So there's kind of like this circle and then a slightly smaller one inside of it, and they keep getting smaller and smaller and smaller, shrinking towards the point of application of loading. The implication is that anywhere along one of these kind of circles, the radial stress has the same value, which is kind of interesting. And as you shrink the size of that circle, that radial stress is still constant along that particular smaller circle, but it's now larger. And it continues to grow until obviously the radius of this circle shrinks to 0. All right. You can represent this in terms of cylindrical polar coordinates and representing the radial coordinate, or we can transform everything into our classical x, y, and z coordinate frames to look at what is the distribution of, xx stress. A little bit confusing because I've actually defined my coordinate frame such that x is pointing straight down and y is actually pointing horizontally. So I can plot things like what's the component of xx stress, the stress directly downwards, tangential stress, and shear stress. Now I want to take a moment and ask you, what's kind of distinguishing about these things? What's sort of interesting? What do you take away from these images? Yeah, right underneath the point of application of this load, there's like these concentrated shear forces inside of the member, basically. So you get sort of these localized shear stresses that occur right underneath the point. Now, does that make good sense? I mean, I would argue yes. You can kind of rationalize it like this. If you had, let's say, some half space and you applied some load on the boundary of it, the deformed shape might look something like this. It'll deflect downward, and maybe a little bit to the left of this, you'll have a ton of shear force going into this localized region. And the same thing over here, a ton of shear force going into this localized region. As you move further away, it dissipates, it kind of like spreads out throughout the rest of the body, but directly under the load, the points adjacent to that loaded point are going to be basically subjected to huge, huge shear forces. So that's one thing. And if you're concerned about things like, I don't know, a bridge, let's say maybe some kind of bridge deck that has some, I don't know, truck moving across it. And you have, let's say, a tire of that truck rolling across the bridge, then directly under, let's say, that tire, which could be idealized roughly as like a point load. Within the bridge deck, you're going to get these very, very localized shear forces directly under or to the left and right of that point load, which basically means you have the risk of something called punch through. It's basically a shear failure where the material just like fails entirely in that kind of mode of shear. And obviously that's a problem. You want to at least make sure that you're abating that. And usually you can get around that by, making some approximations about how you're actually distributing the stress. It's never actually going to be exactly concentrated like this. If you're dealing with, let's say, tires on a roadway, we're talking about, not necessarily a tire applying a point load at this singular location, but most of the time tires are pretty flexible. They have some compliance. So when they compress on the surface of the roadway, they're actually going to deform quite a bit and spread out that load over kind of a deformed area of contact. And that's precisely what we're going to talk about next time, and examine some of these solutions in the context of figuring out how exactly does this relate to the subject of contact mechanics and points of application of loading and how forces are actually transferred between bodies, not necessarily in this singular point-wise area of contact, but rather as distributed areas of contact between two bodies. All right, so until next time, we'll pick up on Thursday.